1912, Detroit, Michigan. The metallurgical report from European spring steel experts would dismiss what American engineers were attempting in a locked 12 by 15-foot room at Ford's Piquette Avenue factory. Vanadium steel springs, heat-treated using methods that contradicted everything European craftsmanship had perfected over centuries of guild tradition. Through the hiss of oil-quenching baths and the glow of precision furnaces, Ford engineer E.F. Lake mapped temperature curves with scientific accuracy that European masters guarded as ancient secrets. No apprenticeships, no inherited techniques passed down through generations, no reliance on craftsman intuition. In European workshops, spring steel masters achieved quality through hand-selecting premium materials and forged tempering using feel, an experience refined over hundreds of years. Each spring carried the unpredictable variations of human craftsmanship. Most failed under the stress of American automobile speeds. The Americans were operating with industrial philosophy the Europeans had declared impossible. Controlled atmosphere heat treatment, mathematical tempering cycles, systematic elimination of metallurgical uncertainty through precision rather than tradition. 8,000 miles from European forges, the most decisive breakthrough in spring steel manufacturing was revealing itself in Lake's systematic experiments, not through centuries of inherited wisdom, but through American scientific methodology that would prove industrial processes could achieve what European craft tradition never imagined possible. The steel fragments scattered across Henry Ford's workbench told a story of European supremacy that American automakers had accepted as unchangeable fact. Each twisted piece of spring steel came from the wreckage of a French racing car that had dominated European circuits for 3 seasons before meeting its end on an American track in 1905. Ford turned the largest fragment over in his calloused hands, noting the fine grain structure visible in the fractured metal. The Europeans had achieved something American metallurgists insisted was impossible with available technology. European carriage springs ruled the early automotive market through sheer engineering superiority that no American manufacturer could match. Hand-forged in workshops that traced their techniques back to medieval guilds, these iron leaf springs carried the weight of tradition alongside their mechanical loads. Master craftsmen in Sheffield, Birmingham, and the Ruhr Valley guarded heat treatment secrets passed down through generations of apprenticeships, creating springs that commanded premium prices across international markets. Each leaf underwent individual attention from specialists who could judge proper tempering by the color of heated steel under forge light, adjusting treatment based on subtle variations in the metal's response to flame and hammer. Yet for all their craftsmanship, European springs failed catastrophically under American driving conditions. The smooth cobblestone streets of London and Paris had never prepared European engineers for the punishment of American roads. Rutted dirt paths, rocky mountain passes, and the relentless speeds that American drivers demanded from their automobiles created stresses that snapped even the finest European leaf springs within months of installation. American automakers importing European spring technology faced constant warranty claims and customer complaints as springs fractured without warning, leaving vehicles stranded and drivers furious. The fundamental problem extended beyond mere durability. European springs weighed nearly twice what equivalent American carbon steel could achieve, adding unnecessary mass to vehicles already struggling with power limitations. Their prohibitive costs meant that only luxury automobile manufacturers could afford them, while companies targeting middle-class buyers remained trapped using inferior American alternatives that satisfied no one. Ford calculated that European spring technology, even if perfected for American conditions, would add $200 to the cost of each Model T, pricing his revolutionary automobile beyond the reach of ordinary working families. When Ford discovered vanadium content in the French racing car's springs, he realized the Europeans possessed metallurgical knowledge that American industry lacked entirely. Vanadium steel represented a quantum leap in materials science, offering strength characteristics that carbon steel could never match regardless of heat treatment refinements. The racing car's springs had maintained their precise camber through thousands of miles of European competition, showing no signs of the stress relaxation that plagued American alternatives. Ford's examination revealed spring rates that remained constant under loads that would have permanently deformed conventional steel within weeks. European suppliers controlled every aspect of vanadium steel production from mine to finished product. Their cartel pricing ensured that American manufacturers would remain dependent on European technical expertise while paying premium costs for materials that Europeans could produce at a fraction of the price. More critically, European experts refused to share heat treatment procedures that transformed raw vanadium steel into superior springs. They offered finished products, but never the knowledge required for American independence in advanced metallurgy. The revelation of vanadium's potential arrived through an unexpected source when Joseph and James Flannery approached Ford with a proposition that seemed too advantageous to believe. The Flannery brothers controlled 92% of world vanadium production through their Peruvian mining operations, yet they struggled to find profitable applications for their massive ore reserves. European customers purchased only limited quantities for specialty applications, leaving the Flannerys with warehouses full of vanadium concentrate and no expanded market for their revolutionary material. Their offer to Ford promised access to unlimited vanadium supplies at cost, provided Ford would develop American heat treatment processes that could compete with European methods. Ford's metallurgist child Harold Wills began secret experiments in a locked room at the Piquette Avenue factory, working with vanadium samples that represented American industry's first serious attempt to break European metallurgical dominance. Wills understood that success required more than simply substituting vanadium for carbon in existing heat treatment processes. The molecular structure of vanadium steel demanded entirely different approaches to heating, quenching, and tempering that no American had ever attempted on production scale. The early results proved devastating to American confidence. Ford's first vanadium springs cracked during heat treatment, confirming European experts' dismissive predictions about American metallurgical capabilities. The failures revealed fundamental gaps in American understanding of advanced steel chemistry that decades of traditional blacksmithing experience could not overcome. Each fractured spring represented wasted material, lost time, and mounting evidence that European supremacy in metallurgy reflected genuine technical advantages rather than mere tradition. European metallurgical authorities declared American efforts doomed from the start, pointing to centuries of accumulated knowledge that American industry could never replicate through crude experimentation. Their published papers emphasized the subtle craft elements in vanadium heat treatment that required generational training to master properly. Master craftsmen argued that vanadium's complex metallurgy demanded intuitive understanding of steel behavior that mechanical processes could never achieve, regardless of American investment in industrial equipment or scientific methodology. The 1908 Model T launched with adequate springs that satisfied customer expectations without approaching the performance levels that Ford knew vanadium technology could deliver. Every Model T rolling off the production line carried springs that represented compromise rather than innovation, accepting limitations that Ford refused to consider permanent. The successful launch provided time and revenue for continued experimentation, but Ford understood that American automotive leadership required mastery of advanced material science that remained exclusively European knowledge. American industrial pride demanded a response to European technical dominance that went beyond importing finished products at premium prices. The challenge extended beyond springs to fundamental questions about American capability in advanced manufacturing. Could systematic American industrial methods overcome European craft traditions that claim superiority through centuries of accumulated wisdom? The answer would determine whether American automobile manufacturing achieved true independence or remained permanently dependent on European technical leadership in critical materials science. The Flannery brothers' chief engineer arrived at Ford's Piquette Avenue factory in January 1908, carrying blueprints that represented everything European metallurgy refused to share with American competitors. Unlike the secretive guild masters who guarded their knowledge through apprenticeship traditions, the engineer spread detailed technical drawings across Ford's conference table, explaining vanadium heat treatment with the precision of industrial science rather than craft intuition. His diagrams showed furnace temperatures, quenching bath compositions, and tempering cycles with mathematical accuracy that European workshops never documented, preferring to rely on master craftsmen's personal experience passed down through generations. Ford's team embraced this systematic approach with enthusiasm that bordered on obsession. Where European methods depended on individual craftsman judgment, American industrial philosophy demanded reproducible processes that any trained worker could execute consistently. Childe Harold Wills established precise temperature measurement systems using pyrometric devices that could detect variations of 5 degrees Fahrenheit, equipment that European forges considered unnecessary complications to established techniques. The Americans treated metallurgy as engineering science rather than inherited art, mapping every variable that affected spring steel performance. The construction of Ford's heat treatment facility proceeded with revolutionary design principles that challenged fundamental assumptions about steel processing. Traditional European forges relied on coal fires and craftsman experience to achieve proper heating, but Ford installed oil-fired furnaces with temperature controls that maintained heat within narrow ranges impossible for manual methods. The facility's ventilation system removed combustion gases that could contaminate steel surfaces during heating, while precision timing mechanisms ensured consistent exposure periods for every piece processed. Each furnace station included measurement instruments that recorded actual temperatures rather than depending on visual color judgment that varied between individual operators. E.F. Lake emerged as the driving force behind Ford's systematic metallurgical experiments, bringing university training in steel chemistry to problems that European craftsmen approached through traditional methods. Lake understood that vanadium's molecular structure required fundamentally different heat treatment than carbon steel, demanding precise control over crystal formation during cooling processes. His laboratory notebooks recorded exact temperatures, timing sequences, and cooling rates with scientific methodology that treated every failed experiment as valuable data rather than wasted effort. While European masters guarded their successful techniques as trade secrets, Lake documented both failures and successes with equal precision, building comprehensive understanding of vanadium behavior under controlled conditions. The experimental process revealed complexity that European guild training had simplified through centuries of trial and error refinement. Lake discovered that vanadium steel's response to heat treatment varied significantly based on ore source, carbon content, and even seasonal humidity changes in the factory atmosphere. Variables that European craftsmen compensated for through experience and intuition required systematic measurement and control in American mass production environments. Each batch of vanadium concentrate from Peru showed subtle chemical differences that demanded adjusted heat treatment parameters, forcing Lake to develop testing procedures that could predict optimal processing conditions for every shipment. Ford's investment in precision equipment paid immediate dividends as Lake's team achieved consistent results that European hand methods could never duplicate. Temperature measurement systems revealed that European traditional heating actually varied by hundreds of degrees between different craftsmen and even different days for the same master. American instrumentation eliminated this variability through mechanical control that maintained exact temperatures regardless of operator experience or atmospheric conditions. Oil quenching baths maintained consistent cooling rates that European water quenching could never achieve, while mechanical timing devices ensured identical treatment periods for every spring processed. The breakthrough came when Lake mapped the complete heat treatment cycle that transformed raw vanadium steel into superior spring material. His process began with heating to 1600 degrees Fahrenheit, precisely controlled to avoid both underheating that left steel soft and overheating that created brittleness. The critical quenching phase required immediate transfer to oil baths maintained at exactly 80 degrees Fahrenheit, creating rapid but controlled cooling that locked vanadium's crystal structure in optimal configuration. Final tempering at 850 degrees eliminated internal stresses while preserving the strength characteristics that made vanadium superior to carbon steel alternatives. Laboratory testing confirmed that Lake's systematic process achieved tensile strengths of 160,000 pounds per square inch, nearly triple the 60,000-pound capacity of European carbon steel springs. More importantly, American vanadium springs maintained consistent performance characteristics across entire production runs, eliminating the quality variations that plagued European hand-forged alternatives. Each spring tested showed identical load-bearing capacity, spring, rates, and fatigue resistance that European methods could never duplicate through individual craftsman attention. The systematic approach had overcome traditional techniques through industrial precision rather than inherited skill. Production implementation proved that American manufacturing philosophy could achieve superior results at lower costs than European craft methods. Lake's heat treatment process required less skilled labor than traditional techniques, since mechanical controls eliminated the need for master craftsman judgment in critical operations. Training periods measured in weeks rather than years, while consistent results eliminated the waste associated with European quality variations. Each American worker could produce vanadium springs with performance characteristics that only the most experienced European masters achieved occasionally through perfect technique execution. The Model T production line began incorporating Lake's vanadium springs in late 1910, marking American automotive industry's first successful challenge to European metallurgical supremacy. Each spring underwent identical heat treatment that eliminated the performance lottery associated with European craft production. Ford's systematic approach had transformed metallurgy from inherited art into reproducible science, proving that American industrial methods could surpass traditional techniques through precision measurement and mechanical control rather than generational training and personal experience. American vanadium springs weighing 40% less than European equivalents carried twice the load while maintaining perfect spring characteristics after thousands of miles of service. The systematic heat treatment process eliminated weak spots that caused European springs to fail unpredictably, creating reliability that hand-forged alternatives could never match. Ford's scientific methodology had achieved what centuries of European craft tradition claimed impossible through mechanical processes alone. Ford's advertising department crafted marketing campaigns that proclaimed American metallurgical victory with confidence that bordered on arrogance. Full-page advertisements in automotive magazines featured dramatic photographs of Model T vehicles navigating rocky mountain terrain that would have destroyed European springs within miles, accompanied by bold headlines declaring vanadium steel, the superiority that built American automobiles. Sales literature distributed to dealerships across the nation emphasized technical specifications that European manufacturers could not match, listing precise tensile strengths and fatigue resistance numbers that demonstrated American industrial science's triumph over traditional craft methods. Each advertisement reinforced the narrative that systematic American innovation had finally overcome centuries of European metallurgical dominance. The Model T's commercial success validated Ford's confidence in vanadium technology as production doubled annually throughout 1911 and 1912. Customer testimonials flooded Ford's offices with praise for spring durability that exceeded all previous automotive experience, with drivers reporting perfect performance after 50,000 miles of service that would have required multiple spring replacements using European alternatives. Dealership mechanics noted the consistent quality that eliminated the performance variations associated with hand-forged springs, while service records showed dramatically reduced warranty claims related to spring failures. Ford's systematic heat treatment had created reliability that traditional methods could never achieve. European automotive journals grudgingly acknowledged American achievements while maintaining that craft traditions remained superior for premium applications requiring absolute quality. Their articles emphasized that mass production techniques, however successful commercially, could never achieve the refined performance that individual master craftsmen delivered through centuries of accumulated expertise. European manufacturers positioned their products as luxury alternatives for discerning customers who valued traditional craftsmanship over American industrial efficiency, maintaining price premiums that reflected their specialized manufacturing approach rather than admitting technical inferiority to systematic methods. Lake's heat treatment process achieved metallurgical perfection that surpassed European hand-forged alternatives in every measurable category. Vanadium springs produced using his systematic methods maintained perfect camber after 60,000 miles of service, showing no signs of the stress relaxation that caused European springs to sag and lose their load-bearing capacity over time. Laboratory analysis revealed crystal structures of exceptional uniformity that eliminated the weak spots responsible for unpredictable failures in traditional springs. The controlled atmosphere heat treatment created metallurgical consistency that European craftsmen could never duplicate through manual techniques, regardless of their skill level or experience. Model T frames constructed with vanadium steel components demonstrated extraordinary structural integrity that revolutionized automotive durability standards. The lightweight yet incredibly strong material allowed Ford to reduce vehicle weight while increasing load capacity, creating performance advantages that European manufacturers could not match without adopting American metallurgical techniques. Crash testing revealed that vanadium frames absorbed impact energy more effectively than traditional steel alternatives, while maintaining structural integrity that protected passengers during accidents. The superior material properties translated directly into competitive advantages that established American automotive leadership in international markets. Ford's confidence in vanadium technology led to aggressive expansion plans that assumed unlimited access to high-quality Peruvian ore would continue indefinitely. Production schedules projected manufacturing increases that would require massive quantities of vanadium concentrate, while marketing commitments promised customers consistent spring quality based on Lake's proven heat treatment methods. The company invested heavily in additional heat treatment equipment and trained workers in systematic procedures that depended on receiving ore with consistent chemical composition from Flannery Brothers mining operations in South America. The disaster struck without warning in late 1912, when a shipment of Peruvian vanadium ore arrived with chemical contamination that Lake's testing procedures failed to detect immediately. The ore appeared identical to previous deliveries, showing correct vanadium content and physical characteristics that suggested normal processing would achieve expected results. Lake's team processed the contaminated material using established heat treatment procedures, creating hundreds of leaf springs that passed initial quality inspections, and entered production inventory destined for Model T assembly lines across the nation. The first spring failures occurred within weeks of installation, creating catastrophic consequences that shattered Ford's reputation for reliability. Springs snapped in half during normal driving conditions, causing sudden loss of vehicle control that resulted in accidents and fatalities across multiple states. Customer complaints flooded Ford dealerships as drivers demanded explanations for failures that contradicted all previous experience with vanadium spring performance. Each broken spring represented not only mechanical failure, but also betrayal of customer trust that Ford had built through years of consistent quality delivery. Investigation teams dispatched to examine failed springs discovered fracture patterns that indicated metallurgical defects rather than mechanical overloading or improper installation. The breaks occurred at stress concentration points that should have been eliminated by Lake's heat treatment process, suggesting fundamental problems with the steel's crystal structure that systematic procedures had failed to prevent. Microscopic analysis revealed contamination effects that European hand selection methods might have detected through individual piece examination, but American mass production techniques had missed entirely. European metallurgical experts seized the opportunity to declare vindication of traditional craft methods over American industrial approaches. Their published analyses of the failed springs emphasized that mass production techniques could never achieve the quality control that individual craftsman attention provided through centuries of proven methods. European trade journals featured detailed critiques of American systematic approaches, arguing that metallurgical precision required human judgment that mechanical processes could never replace, regardless of investment in scientific equipment or measurement systems. The technical investigation revealed that microscopic sulfur contamination in the Peruvian ore had created weak spots in vanadium steel's crystal structure that Lake's heat treatment process could not eliminate. European master craftsmen historically compensated for such contamination through selective material rejection and adjusted heat treatment based on visual and tactile assessment of individual pieces during processing. American systematic methods, designed for consistency across large production runs, lacked the flexibility to adapt to subtle material variations that hand methods could accommodate through experienced operator judgment. Ford faced the devastating reality that American industrial confidence had been built on assumptions about material quality that proved unreliable when subjected to real-world variations. The company's reputation for superior engineering lay in ruins as customer lawsuits mounted and competitors exploited the failure to question American technological leadership. Lake's systematic approach, which had seemed to represent triumph of scientific methodology over traditional craft techniques, suddenly appeared inadequate for the complexities of metallurgical production in an imperfect world where ore quality could vary unpredictably despite all precautions. Lake's investigation into the spring failures began with systematic analysis that treated each fractured component as forensic evidence rather than manufacturing waste. His laboratory team sectioned failed springs at precise intervals, polishing cross-sections to reveal internal structure under high magnification microscopes that European craftsmen never possessed. The examination revealed microscopic inclusions distributed throughout the steel matrix like tiny bombs waiting to propagate cracks under stress. These sulfur-bearing particles, invisible to naked eye inspection that European masters relied upon, created stress concentration points that no heat treatment could eliminate once they became embedded in the metal during initial processing. The contamination source traced back to the Peruvian mining operation, where sulfur-bearing ore had mixed with pure vanadium concentrate during extraction or transportation. Lake's chemical analysis revealed sulfur content of 0.03% in the contaminated batch, compared to 0.005% in previous shipments that had produced successful springs. This seemingly insignificant difference created catastrophic effects during heat treatment, as sulfur compounds formed brittle phases that remained stable at normal tempering temperatures but failed instantly under mechanical loading. European hand-forging methods historically avoided such problems through selective rejection of contaminated materials, but systematic American processing had no mechanism for detecting these subtle chemical variations. The revelation that European craftsmen possessed intuitive knowledge for identifying contaminated materials through sensory evaluation challenged fundamental assumptions about industrial methodology. Master smiths examined raw steel by fracturing small samples and evaluating grain structure, color, and even smell to detect impurities that chemical analysis might miss. Their centuries of accumulated experience included recognition patterns for sulfur contamination that manifested as slight discoloration or unusual spark patterns during forge heating. American systematic approaches designed for efficiency and consistency had eliminated these human evaluation steps in favor of standardized procedures that assumed uniform material quality. Lake refused to accept that European craft methods possessed inherent advantages over systematic industrial processes, instead viewing the contamination problem as a challenge requiring enhanced American scientific methodology. His response involved developing spectrographic testing procedures that could analyze our chemistry with precision far exceeding European sensory evaluation capabilities. The spectrographic equipment, recently developed for astronomical research, could detect trace elements at concentrations below human perception thresholds while providing quantitative measurements that eliminated subjective judgment from material acceptance decisions. Implementation of rigorous ore testing revealed the full scope of material quality variations that European methods compensated for through selective use and adjusted processing. Each shipment from Peru showed subtle differences in sulfur, phosphorus, and carbon content that affected optimal heat treatment parameters, forcing Lake to develop adaptive procedures that modified processing conditions based on actual chemistry rather than assuming uniform composition. The systematic approach evolved beyond simple standardization to become responsive methodology that maintained consistent output despite variable inputs. The breakthrough innovation emerged from Lake's recognition that controlled atmosphere heat treatment could eliminate contamination effects that conventional processing could not address. Traditional European forges exposed heated steel to combustion gases that potentially added impurities during processing, while American industrial furnaces typically used ambient air that contained moisture and oxygen that could react with steel surfaces at high temperatures. Lake designed sealed chamber systems that heated vanadium steel in precisely controlled gas environments that prevented atmospheric contamination while promoting chemical reactions that neutralized existing impurities. The controlled atmosphere process required engineering innovations that pushed American industrial capability beyond existing standards. Lake's team constructed furnace chambers with gas-tight seals that maintained internal atmosphere composition throughout heating cycles, while sophisticated gas mixing systems provided exact concentrations of hydrogen, carbon monoxide, and inert gases that optimized steel chemistry during processing. Temperature control systems maintained heating profiles within 5-degree tolerance, while pressure regulation prevented atmospheric infiltration that could compromise the controlled environment. Testing the new process demanded patience that conflicted with Ford's urgent need for production recovery, but Lake insisted on thorough validation before resuming spring manufacturing. Each experimental batch underwent comprehensive mechanical testing that exceeded European craft standards, including fatigue analysis that simulated years of service conditions within weeks of laboratory time. The controlled atmosphere treatment eliminated sulfur-bearing inclusions through chemical reduction reactions that converted contaminating compounds into harmless phases that integrated seamlessly with the steel matrix. Results exceeded expectations as controlled atmosphere processing created metallurgical structures superior to anything European hand methods had achieved. Springs treated using Lake's enhanced process showed tensile strengths approaching 180,000 pounds per square inch, representing improvement even over previous American successes with uncontaminated materials. More importantly, the process eliminated quality variations entirely, producing springs with identical performance characteristics regardless of minor ore chemistry differences that had caused the catastrophic failures. Lake's innovation addressed contamination through systematic chemistry control rather than selective material rejection, creating methodology that could handle imperfect raw materials through processing excellence rather than depending on perfect inputs. The controlled atmosphere chambers neutralized sulfur contamination while promoting grain refinement that enhanced mechanical properties beyond levels achievable with conventional heat treatment. American industrial science had evolved to overcome material limitations through process sophistication that European craft methods could never match. Ford's production resumption using Lake's controlled atmosphere process restored customer confidence while establishing new performance standards that European manufacturers could not approach. Each spring received identical treatment in sealed chambers that eliminated atmospheric variables, human judgment errors, and contamination effects that had plagued previous methods. The systematic approach achieved consistency that hand methods could never duplicate, while surpassing traditional quality levels through scientific control over every processing variable. The enhanced methodology represented fundamental advancement in metallurgical science that transformed American manufacturing philosophy. Lake had proven that systematic approaches could overcome raw material imperfections through process excellence, eliminating dependence on perfect inputs that European methods required. Controlled atmosphere processing became the foundation for American metallurgical leadership that would extend far beyond spring manufacturing into every aspect of steel production requiring superior quality and absolute reliability. American industrial science had evolved beyond European craft traditions through innovation that enhanced rather than replaced systematic methodology. Lake's presentation to the Society of Automobile Engineers in Detroit drew an unprecedented audience of metallurgists, engineers, and industry leaders who gathered to hear American solutions to problems that had challenged European expertise for centuries. His paper, titled Heat Treatment of Leaf Springs, detailed exact temperature curves, quenching rates, and controlled atmosphere compositions with scientific precision that transformed metallurgy from craft tradition into reproducible engineering discipline. The presentation included microscopic photographs showing crystal structures achieved through systematic processing, chemical analysis data proving contamination elimination, and mechanical test results demonstrating performance superior to any European alternative. Lake's methodology replaced centuries of guild secrecy with open documentation that any qualified engineer could implement. The technical details Lake shared represented revolutionary advancement in metallurgical science that established new standards for industrial processing worldwide. His controlled atmosphere chambers operated at precisely controlled temperatures between 830 and 860 degrees Celsius, maintained through pyrometric feedback systems that adjusted heating automatically to compensate for thermal variations. The gas mixture composition consisted of 15% hydrogen, 10% carbon monoxide, and 75% nitrogen, creating reducing atmosphere that eliminated sulfur contamination while promoting optimal grain structure formation. Oil quenching followed immediately after atmospheric treatment, cooling springs at rates calculated to achieve specific crystal formations that maximize strength while eliminating brittleness. The tempering process that completed Lake's methodology required mathematical precision that eliminated guesswork from final spring characteristics. Tempering temperatures between 400 and 500 degrees Celsius removed internal stresses while preserving the strength advantages gained through controlled atmosphere processing. Timing sequences measured in precise minutes, rather than craftsman judgment, ensured consistent results across entire production runs, while temperature monitoring prevented both undertempering that left springs brittle and overtempering that reduced strength below specification requirements. Each spring received identical treatment that guaranteed performance uniformity impossible with traditional hand methods. Model T production incorporating Lake's perfected springs demonstrated reliability that redefined automotive durability standards throughout the industry. Springs manufactured using controlled atmosphere processing maintained perfect load-bearing capacity after hundreds of thousands of miles, showing no signs of stress relaxation or fatigue cracking that affected European alternatives. Customer reports documented springs lasting entire vehicle lifetimes without replacement, while dealership service records showed virtual elimination of spring-related warranty claims. The systematic methodology had created metallurgical excellence that exceeded customer expectations while reducing manufacturing costs through elimination of quality variations and rework requirements. Ford's advertising campaigns promoted the technical achievement with marketing materials that educated customers about metallurgical innovations rather than simply claiming superiority. Detailed brochures explained controlled atmosphere processing in terms accessible to educated consumers, emphasizing scientific methodology that guaranteed consistent performance rather than depending on craftsman skill variations. The educational approach built customer confidence in American industrial capability while positioning Ford as technology leader whose innovations benefited from systematic engineering rather than traditional manufacturing approaches. Sales literature included actual test data and performance specifications that competitors could not match through conventional methods. European manufacturers responded to American metallurgical leadership with reluctant acknowledgement that systematic industrial processes had achieved results beyond traditional craft capabilities. Technical journals published analyses of Lake's methodology that admitted American innovations represented genuine advancement in steel processing science, despite European resistance to abandoning centuries of established techniques. Some European firms attempted to implement controlled atmosphere processing using American specifications, but lacked the precision equipment and systematic training required for successful adoption. The gap between craft tradition and industrial science had widened beyond European ability to close through incremental improvements. The long-term validation of Lake's process emerged through decades of field performance that proved systematic methodology superior to any alternative approach. Model T springs manufactured between 1913 and 1920 using controlled atmosphere heat treatment continued operating perfectly after 100 years of service, maintaining original spring rates and load capacity despite accumulating hundreds of thousands of miles. Museum vehicles equipped with Lake's springs demonstrated metallurgical stability that modern manufacturing could not duplicate, even with advanced equipment and improved raw materials. The controlled atmosphere process had achieved metallurgical perfection that subsequent cost-cutting measures consistently failed to match. Modern spring manufacturing, driven by economic pressures rather than engineering excellence, abandoned Lake's controlled atmosphere methodology in favor of automated systems that reduced processing costs while sacrificing quality standards. Contemporary springs lose 30% of their tension within 30,000 miles, requiring replacement at intervals that would have been considered manufacturing failure during Lake's era. Recycled steel containing unknown contamination levels replaced the pure materials that Lake's process was designed to purify, while automated heat treatment systems lacked the precision controls necessary for optimal metallurgical results. Cost reduction priorities eliminated the systematic quality controls that made American springs superior to European alternatives. The contrast between Lake's controlled atmosphere springs and modern alternatives demonstrated the consequences of abandoning systematic engineering excellence for economic convenience. Original Model T springs maintained precise metallurgical structure through controlled processing that eliminated contamination while optimizing crystal formation, creating durability that exceeded design expectations by factors of 10 or more. Modern springs, manufactured using simplified processes with contaminated recycled materials, exhibit the same performance degradation that plagued pre-Lake American manufacturing when systematic quality control was considered unnecessary expense. The abandonment of controlled atmosphere methodology returned spring manufacturing to quality levels that Lake had definitively surpassed through scientific innovation. Lake's legacy extended far beyond spring manufacturing to establish principles of systematic metallurgical control that influenced American industrial development throughout the 20th century. His methodology proved that scientific approaches could overcome raw material limitations, environmental variations, and human inconsistencies that traditional craft methods could never eliminate reliably. The controlled atmosphere concept found applications in aircraft manufacturing, precision tooling, and specialty steel production, where quality requirements demanded systematic processing rather than craft tradition. American metallurgical leadership traced directly to Lake's demonstration that industrial science could achieve superior results through systematic methodology that eliminated the variables and uncertainties inherent in traditional approaches. The enduring performance of Lake Springs provided tangible evidence that systematic American industrial methods had definitively surpassed European craft traditions through scientific innovation rather than inherited techniques. His controlled atmosphere process represented triumph of engineering, methodology, over traditional approaches that depended on human skill and material selection rather than systematic quality control. American industrial science had evolved beyond European capabilities through innovations that enhanced rather than replaced systematic approaches, creating manufacturing excellence that traditional methods could never achieve consistently or economically.